Voy a bajar el volumen para evitar.
Tú, Roberto, eres profesor asistente de la Federico. ¿Asistente de la Federico?
Listo. Okay, let's start. Good morning, everyone. My name is Marco Rivera. I'm a professor from the University of Talca in Chile. And today I would like to give a brief presentation of Professor Jorge Morales, Professor Diego Celentano, and Professor Roberto Leiva, who are the invited speakers for this session in the online meetings of the Worldwide Energy Network. Professor Jorge Morales, I would like to ask you to start your presentation and to introduce your speakers.
Yeah, thanks everyone for coming. I hope this will be a very short presentation. My name is Jorge Morales. I'm a lecturer professor at the Universidad de Talca. And I will introduce my panelist, Professor Diego Celentano. He is a full professor from Pontificia Universidad Católica de Chile. And Professor Roberto Leiva, he is an assistant professor from the Universidad Federico Santa Maria. That's right. Yeah, that's right. And yeah, I have a little problem with my connection. I will turn off my camera and I will start my presentation, okay? It's good?
Okay.
Okay, give me on 1 second. Okay. You can see my presentation, right?
Not yet.
Now?
Yes, I can see your presentation.
Yes? Okay. Check the names here. Okay. Oh, yes, nice. Okay, the name of this presentation
yes,
is
Numerical.
Yes, no. Okay, okay, I can start right now, right? Yeah. Okay, my presentation is Numerical Study of Electron and Phonon Transport in Crystalline Material. This topic's a hard topic, but it's a little complicated, but I'm trying to show you some applications on one project that I did a few years ago. And first, my outline on this presentation is my motivation, why I study these topics, and the background, one project, and some applications. With the, I think my focus will be in the applications. Why this is important? I think the global energy consumption growth is slow in 2019. Close to 0.6% compared to an average 2% per year over the decades 2000-2018 period. I think in a context of slower economic growth, energy consumption increases at a slower pace than in previous years in China, for example, for 3.2%, when the world largest consumer since 2009, sorry, in Russia is 1.8%, and in India is 0.8% only. But I think what is the challenge in this case is we need more clean energy, and that will be the expectation for the world, I think. And we expect that the energy demand increase in the next period, a third, but 2/3 of the world population in 2040 live in countries with average energy consumption. I think it's still less than 100 gigajoule per head. Another thing is carbon dioxide. Then the emissions from energy use continue to edge up, increasing by almost 10% by 2040. rather than falling substantially. But I think the more energy scenario represent a halfway step to reducing the proportion of the world's population living in countries where the average level of consumption is below 100 gigajoule per head to 1/3 by 2040. The rapid transition scenario represents a similar halfway step on carbon emissions, reducing this emission by around 45% by 2040. I think this is the challenge for all. And on the other hand, renewable energy grows strongly with its share in global power markets increasing substantially, where both wind and solar power grow rapidly, increasing by a factor of 5 and 10 respectively, accounting for broadly similar increments to global power. This rapid growth is aided by continuing pronounced falls in the cost of wind and solar power as they move down their learning curves. However, one interesting topic for me was a study a few years ago how I can represent this both energy and maybe some materials that can combine together and improve some use of clean energy, and that was the study of the study of electron and phonon interaction, for example, and that is well known that the electron phonon coupling plays an important role in governing the electronic transport properties. For a long time, was generally assumed that the lattice thermal conductivity of a given material is independent of the electronic properties, for example. However, since this study of electron phonon coupling has a significant effect on the electronic transport property, and this should also have certain effect on the phonon transport. For example, for the engineer who designs cell phones, solar panels, and computer chips, it's increasingly important to be able to control that way it moves through the crystalline materials, such as silicon, for example. A few years ago, Professor Gang Cheng from MIT said to understand how heat is spread through a material, consider that heat as well as sound. It is actually the motion of vibration of atoms and molecules. Low frequency vibration correspond to sound, while higher frequency correspond to heat. And at each frequency, quantum mechanics principle dictate that the vibrational energy must be a multiple of a basic amount of energy called quantum. And in that sense, he understand and said the phonon is just a fancy word for a particle of heat. And but for me, it was interesting to understand that, and in this figure, for example, I can show you what is the complicated topics and the fundamental topics that I studied before. For example, my concentration was in electron energy, phonon energy, and the energy transport, transformation, kinetic, and resonance, for example. But the transport and transition of principal thermal energy carriers are in this figure I show you. And for example, size effect and the inclusion of various phonon, electron, fluid particle, and photon energy transport transition kinetics in the macroscopic energy. I just said some equation here, connect heat transfer physics and to its application in some cases. And for me, one application that involves all of this concept was in a specific topic in thermoelectrics. And thermoelectric power generation is one of the current interests in clean energy research. For example, in view of direct solar power generation. thermoelectric becomes an attractive application in not only in solar, of course, but in other aspects, for example, in wearables and sensor, etc. Recent research analyses were proposing in the open, for example, literature to cover various aspects of energy generation. Maximize the temperature difference between two sides of thermoelectric device by increasing the heat flow through thermoelectric devices, enhancing material thermoelectric characteristics, seeking, for example, more suitable thermoelectric materials, such as nanometer materials, is one of the most useful and effective way to improve thermoelectric conversion now. Implementing effective heat dissipation on the cold side so that thermoelectric materials can work in the most suitable temperature range, for example, is another kind of applications. And I think one of the most promising technologies that could pave the way for greater gains in energy harvesting are thermoelectric modules, for example. And possible thermoelectric energy harvesting use are vast, as they could be deployed to power everything from off-grid sensors, for example, in remote areas, to refrigerators. And but this is not new. The discovery of thermoelectric was more than 200 years ago, and the names of these effects come from the names of the people that discovered them in the early to mid 18th. For example, in 1921, Thomas Seebeck discovered two different metals are connected at their free ends to form a loop, and one of the two connection points in heat, a nearby compass will deflect. In 1834, Peltier discovered two different metals bars are connected at their free ends to form a loop, and an electrical current is supplied within the loop. One connection between the two metals will absorb heat, and the other connection will release heat. And in 1851, William Thomson, known as Lord Kelvin, discovered if electric current is passed through a bar of metal and the metal bar has a temperature gradient from end to end, heat will be either absorbed or released along the length of the bar. And that is known as Thomson effect. Then this concept is not new, but some advantages of these thermoelectrics are very interesting. For example, this is a solid state. There are no moving parts with this kind of material. This leads to increasing reliable and long life, and cooling and heating in one device. Other cooling methods require a separate heating system. With this kind of material, change polarity, change cooling or to heating, and vice versa. No greenhouse gas required. Thermoelectric use no refrigerant or greenhouse gases, and this is a positive, for example, for an environment. It's friendly environment. And scalability, thermoelectric cooling and thermoelectric power generation is very scalable from less than 1 watt of cooling power or power generation up to kilowatts, for example. Precise temperature control, electric current provided to the thermoelectric cooler can be precisely controlled. The temperature of a thermoelectric cooler is dependent of the current provided to it. And efficiency, I think, but we can discuss now of this topic because I think we need to improve the efficiency to work with this kind of materials. This is a very good challenge. And the basic block of thermoelectric semiconductor is a semiconductor couple, one N-type and one P-type semiconductor, and that are soldered to copper interconnects as you see in this picture. And how thermoelectric works. Okay, here we have the left hand the thermoelectric generator, and the right hand thermoelectric cooler. The two thermoelectric effects Seebeck and Peltier occur due to the movement of charge carriers in thermoelectric materials. In N-type materials, the charge carriers are electrons. In P-type material, the charge carriers are called holes. And holes are vacancy in a crystal structure in which an electron could, for example, occupy this in some position of this crystal structure. And in the thermoelectric generator, for example, charge carriers diffuse away from the hot end, build up charge at the cool end, produce a voltage potential. And this voltage potential will drive current in a complete circuit and produce power. On the other hand, in the Peltier effect, rather than having, for example, a resistive load in the circuit, a direct current source is used in its place to move the charge carriers by use of an electric field. When these charge carriers move, they take heat with them. Electrons moving to a higher energy level absorb heat, and electrons that move to a lower energy level release heat. And this movement of charge carriers can be used to pump heat against the direction it naturally flows and produce cooling and heating. And interesting is analyze the thermoelectric properties, where the key is the figure of merit, this ZT, and that is the combination of the three key properties. One of this is Seebeck coefficient, and another thing is another property is electrical conductivity, and the last is thermal conductivity. This figure of merit is the primary measure of material performance. And of course, enhancing this, the CT required optimizing the adversely independent, that is electrical conductivity or resistivity, Seebeck coefficient, and thermal conductivity. In this case, thermal conductivity, we can open this kind of property in two. One related with heat transfer by electronic thermal conductivity, and another one is related with lattice vibration by phonons that permit the heat transport. And to found a material with interesting properties to become a thermoelectric, you need a better combination of these properties. And this is a difficult task. As if you see the figure, okay, the better combination is hard, because, for example, if you work with a carrier concentration between 10 to the 18 and 10 to the 21, when carrier concentration increase, for example, Seebeck coefficient decrease, and parallel electrical conductivity increase and electronic thermal conductivity increase too. And in majority of cases, engineers are working separately. In one hand, you can work with the power factor, the combination of square of the Seebeck coefficient and the electrical conductivity, and separately the thermal properties like thermal conductivity. I think the major focus at this moment is only in the thermal process, like thermal conductivity. And currently, the efficiency of thermoelectrics is lower than other energy conversion technologies because of the low performance of the thermoelectric materials. This is a very interesting challenge, because we can found some ZT, figure of merit, in some materials, a combination of materials between 0.5 to 2.5 or 3. But that is not enough, if you see this figure, to replace, for example, other kind of energy, clean or not. And then I think a very good choice is work together, thermoelectrics with the natural energy or renewable energy today. In this figure, most state-of-the-art thermoelectric materials have their maximum figure of merit values between 1 and 1 or 0.5 to 2.5. And that I explained before due to the adversely independent Seebeck coefficient, electrical conductivity, and thermal conductivity. And I think from an efficiency standpoint, set the value close to 3 to 4 that is needed for a thermoelectric to compete with other energy generation technologies. But until now, this has been impossible to achieve. I think only a few materials, but only in laboratory. And okay, that's a little brief of background. And I would like to show you a few slides of one project that I developed before. In that case, this case, I use some methodology that I use for our calculations. This is numerical simulation that I use quantum espresso based on first principle density functional theory calculations and Boltzmann transport theory. If you see the left hand was developed to calculate electronic properties, and the right hand I used before to calculate thermal properties. Okay, both the combination of both, we can obtain the figure of merit in this case. This project is first principle calculation of thermoelectric properties of 4 and 6 chalcogenide 2D materials. And why these 2D materials, advanced materials have the potential, I think, a very good potential that was a few years ago, 2000, I think, at Manchester University, that they were the pioneer of the study and work with 2D materials such as graphene. And graphene was the world's first 2D material, has opened the doors for the exploration of other. And one reason of many research groups focus on 2D materials is because of the unique collection of properties that the material exhibit. For example, 2D version of silicon, phosphorus, phosphorin, and some of carbon's other neighbors in the periodic table are semiconductors, and with band gaps and other electronic properties that in principle can be tuned more easily than they can in the bulk materials, for example. And in this study, I worked with 6 materials, 4 of them with orthorhombic crystal structure, and 2 of them with hexagonal crystal structure that you see here in the figure. And we calculate all of the thermoelectric properties, Seebeck coefficient, electrical conductivity, power factor, electronic thermal conductivity, and lattice thermal conductivity. And the Seebeck coefficient, as you see here, the absolute values of Seebeck coefficients exhibit a decreasing trend with temperature at 10 to the 18 and 10 to the 19, this current concentration, with the exception for tin sulfide, where the change is small. And for a tin selenide, you see here, well, I didn't mention the material. This is germanium sulfide, germanium selenide, tin sulfide, tin disulfide, tin selenide, and tin diselenide. Where for the tin selenide, where the absolute value is increasing slightly at the 10 to the 19. But at the 10 to the 20, an increasing trend for all T materials in the Seebeck coefficient in absolute values is observed. And due to the interrelationship between current concentration and Seebeck coefficient, we notice as doping level increase, the Seebeck coefficient decrease, in some cases dramatically. Okay, another thing is electrical conductivity, where the electrical conductivity has the same increasing trend for all the materials as a function of temperature. And this will be explained as the temperature increase, more electrons are excited, and thus the electrical conductivity increase. We combine both the Seebeck and the coefficient and the electrical conductivity, and we can calculate power factors. And the same trend of electrical conductivity, power factor increase as a function of temperature, where tin disulfide and tin diselenide have higher values of power factor. And this could be some impact in the ZT equation. If you remember, ZT is power factor over the thermal conductivity. And if we expect more higher values of power factor, we can maybe we can we will obtain more better values of CT. However, we need to calculate before the I will pass this, the lattice thermal conductivity. And in this case, the lattice thermal conductivity was decreased monotically, and this is because a temperature increase and an harmonic phonon scattering becomes more intensive. And all of the 2D materials studied here have relatively low thermal conductivity if we compare with other kind of materials like graphene and molybdenum diselenide, bursite disulfide, and others. And making them promising candidate to have a higher ZT that is explained. However, in this case, you can see here, combining the all calculated thermal electrical properties, we can obtain that I mentioned before, the dimensionless ZT, of course, as a function of temperature. And among all of the 2D material studies from 300 Kelvin to 800 Kelvin, the best figure of merit value was for tin selenide. Okay, disregard of doping level. So in all of doping level was the same results. Tin selenide was the best. Okay, and in this study, as a conclusions, the DFT and the Boltzmann transfer equation model was used to calculate the thermoelectric properties for this list of materials. We determined the electronic bands, would not show you in this case, and Seebeck coefficient, and with and without the spin-orbit coupling. And the best material in this case was tin selenide. And this was interesting because tin selenide I think was the most material study in the last 5 or 6 years, and with very good results. It's a promising candidate to the thermoelectric for thermoelectric applications. And some applications are related with we can separate power generation and cooling and heating applications. In that case, we have an extreme environment, for example, power generation for remote areas, for pipelines, for head offshore platforms, etc. Waste heat recovery, microgeneration for sensor and electronics, and combined heat and power system, for example, solid some application with solar power, for example. And on the other hand, cooling and heating application, refrigeration with the small refrigerators, meaning vehicle refrigerators, electronic cooling, electronics and CPU cooling, telecom cooling devices, etc., air conditioning, and thermal comfort. And in this case, we can see here, for example, one application is sensors, where we can see the application with the body, using the body temperature and generate some millivolts, for example. And another thermoelectric innovation is this kind of devices that I can show you here, and of course, while sensing another. But here is they are selling this kind of bracelet. The wave bracelet is a little expensive. This bracelet activates your thermal sense and connected to your perception of temperature with cooling and warming sensations, for example. You can buy it if you want. Another is in energy with a solar TE generator, TE is Thermoelectrics generator, where you can combine solar concentration, for example, in this figure, or with a flat panel in this figure, or with a curved panel in this figure, with the different configuration of solar energy. And of course, in a car, for heating or cooling the seats, for example, another kind of applications. And finally, interesting for me, for example, is the application in medicine, where you can find cooling and heating devices, chiller, warmer, cools, and or heats of liquids, therapeutic application, therapeutic condition, and another example of wearable sensors for electroencephalography, electrocardiography, pulse oximeters, etc. Okay. And I don't know how long time was my presentation, but my acknowledgement of course, for my panelists, for this kind of online meetings of the name is Worldwide Energy Network. Thanks very much, Marco, for this invitation. The Universidad Talca, Universidad Católica, and University of Notre Dame. And
hello.
Research and nanotechnology materials. Okay, thanks very much.
Thank you very much, Jorge. I would like you to stop sharing your screen, please.
Yes, let me 1 second.
And we thank you very much for your very interesting presentation, and it is related to your field of research. And I would like to give a space to the panelists to comment the presentation of Jorge. And for this we have as panelists, as Jorge already presented them, to Diego Celentano and Roberto Leiva. Maybe Diego and Roberto, please, can you connect your webcams and your microphone, please? And we'd like you to comment the presentation, please. Diego, please. Yes, you have all...
Thank you, Jorge. Thank you, and thank you, Jorge, also for the talk. Just looking at your results in terms the figure of merit in terms of temperature, that means that probably the most interesting application in terms of efficiency is to use this material at high temperature. This is possible, this is interesting, or there are some practical problems there?
I think you have two choices, to use material at lower temperature, for example, at room temperature, that is interesting for application. And another thing is using for the high temperature, for example, with like oxide materials, perovskite, and another kind of material that can work very good with a better stable chemically at a higher temperature. It depends what kind of application do you want in this case. And of
Okay.
course, we need to try to find materials with higher values of ZT in that case. Okay, the problem, I think, a little problem now is to find materials and thermoelectric materials with higher values of ZT, because it's different if you work in the laboratory or you work in the real life. You see, and producing this kind of material for industrial application, for example.
Okay. One option could be the, probably you work on this, the dopage of materials, for instance.
Yeah, this maybe could be interesting if you change some structure in this material. I'm talking in the crystal structure, for example, doping or generative vacancies. You can improve some properties, transport properties, like for example, electrical properties or thermal properties. And of course, if you improve thermal properties, for example, with lower values of thermal conductivity, in that case, you can have better results for ZT, or in opposite way, if you have better results in electrical property, you can, of course, found better results for ZT. But the combination of both is complicated for now.
Okay.
I'm not sure if it exists one material with a better combination of two kinds, power factor and the thermal conductivity.
Yeah. And the last question, more general. The applications you show in the last part of your presentation are really potential applications, or really they are already implemented in real life?
I think, okay,
which is
you
the
see
degree of maturity of them?
Yeah, you see the web bracelet that they are selling in the web, but
Okay.
but another interesting application now is in space, because the NASA, all the radio isotope and some robots, for example, that go to the space, then they have a module of thermoelectric materials, you see, for our own energy in that case. And I think that is a very good application for now.
Okay, okay. Okay, thank you, Jorge.
Roberto, yes, please. Roberto Leiva, please. Can you connect your microphone, please?
Yes, okay. Hi, Jorge.
Hi, Roberto.
According your experience, what is the difference between the direct solar thermal power generation technologies and the use of this technology, also your technology?
Oh, it's not my technology, but yeah, I think the thermoelectric need to improve a lot because they don't work alone without other kind of technology. For example, the solar technology. You can work together, but the problem in this kind of material is the efficiency. The efficiency is lower than 10%, for example. And if you can combine this kind that I show you, the one application is solar thermal concentration of flat panels. You can work together, you see. But if you can work only with thermoelectric, maybe you need a lot of thermoelectric modules to have interesting efficiency. I think this is a barrier today. I think it's a challenge. Yeah.
Okay, but in the case, for example, when you hybrid the different technology to produce power, in this case, what is the main barrier for this technology?
What is the main barrier? Efficiency.
Only efficiency and cost.
I think so. The cost is not high. You have some material that is expensive in the earth, And to make this kind of material is not very complicated. It's easy. I think the different kind of method, chemical vapor deposition, physical vapor deposition, or with solid state, you can work. And the advantage is to work with this kind of material is high. You see solid state, you don't need maintainability and others.
Okay, and in this case, the photon glass electron, what is the effect to improve this technology?
That is a very good combination to improve the transport properties. That is the phonon glass. I think it's one of the better kind of combination to prove this kind of properties that I mentioned before, Seebeck and electrical conductivity and thermal conductivity, for example.
Okay, thank you very much.
Hey, thank you very much for your questions, Diego and Roberto. And we have some questions related mainly to application of this technology, Jorge. And maybe you can answer, and maybe Roberto or Diego is. But for example, it is clear that in the world there is growing demand for clean energy. You show that in your presentation. Additionally, you mentioned that waste heat can be captured by these thermoelectrical property materials that have these properties. Okay. Mm-hmm. How do you think that the development of this application has been, for instance, applied to something that, in my case personally, and the thing we do in the university, applied to solar energy, for example? How
the waste heat
can improve that performance in some way?
The waste heat?
Yeah, to capture that waste heat.
The capture. Oh, okay. Yeah, this is an interesting question because I'm trying to work from a few years ago, and I discussed this with my advisor in the US because, for example, in computers, you can use waste heat maybe to convert to electrical energy, or yes, using this kind of waste heat from another application from cars, for example, or in industrial thermal applications, for example, boilers, turbine, etc. But at this moment, I didn't see this application in a real world, you see. But maybe I think this could work. For me, it's an interesting topic to develop, of course. And on the another hand, is in opposite way is for cooling system. For example, you are in applications in solar power is interesting with PV, for example, applications. And I don't remember here the name. Even Marco can help me in converters, right? In energy converters for electromobility application where you need a very good cooling system, for example, maybe it could be help in this case.
Roberto and Diego, have you got any comments about that?
Sorry. No, it's okay. It's okay for me. Yeah. Maybe we can give some time to the audience to ask some question.
Yeah. We are actually, that's the idea. The audience writes down the question in the chat. We got from YouTube as well and Twitter, and the idea for me that I'm doing those questions for you in order to try to be, to tidy up this thing,
Okay.
There is another question that maybe is interesting. What is the current trend in doing research in silicon nanowires?
I'm doing work with the silicon nanowires now. I'm working with that materials that I show you in the presentation. And another kind of materials, niobium diselenide, for example, vanadium dioxide, and another kind of semiconductors, metals, and superconductors materials, but not with nanowires yet.
Okay, okay. Thank you, Jorge. Let me maybe to be some kind of a, I want to ask you again about the solar energy and solar applications. It is well known that currently regular solar cells have an efficiency of up to 47.1% more or less of efficiency. And this applies for a multi-junction concentrator solar cell, So there is still a lot of wasted heat coming from photons, How can those analyzed materials play an important role to increase these efficiencies?
I think so. Yeah, I think so. We can coupling with this kind of material, that kind of technology. Maybe we can use use that waste heat and maybe convert to electrical energy. Or I think it's an interesting topic. I'm working now. I'm with some application in thermophotovoltaic cells. I'm trying to understand how this can work together with thermoelectric materials, for example. Some researchers just published some papers on that topics, and I think it's very interesting to try to maybe with some simulation you can work that. It's not complicated, but for me it's interesting now, not only working with the simulation to understand the behavior, maybe to do some experiments for me, and I think for you guys in electrical engineering, almost is very interesting to do.
Jorge, I'm very curious about the, how a thermophotovoltaic cell could be. Could you show us something here? Because it's.
I'm not. I not have here now, but I can promise to show you maybe in a short future, maybe close future. But now I don't have nothing here.
No problem.
Sorry about that.
Okay, there is another question that comes from Carlos Rodriguez. Can you tell us, and Roberto and Diego can respond this? Can you tell us about toxicity of these materials as well as the scarcity? Scarcity is a very hot topic around the world about these new materials, especially with those physical properties. For example, selenium and tellurium. Maybe how these issues may affect, the work on this field. Did you get the question about to do some comments about toxicity and availability? Because maybe those materials may be very scarce around the world.
Yeah, I don't know if Diego or Roberto or me. Yeah, whatever. And
Okay.
Jorge,
Okay, yes, Carlos is right. For example, selenium and tellurium both are toxicity. The toxicity and of this material is interesting. It's complicated. But I understand maybe this could be a little problem or a problem. Maybe affect the work in this topic. Yes, is right. But exists another kind of materials that could be worked very well, and with this both material that have very good properties. Maybe the study at this moment is interesting, but I'm trying to work with another kind of material that the toxicity and the scarcity is not a problem for now. But you're right. Yes, this is a big problem maybe today.
Okay,
Yeah.
I don't know if the scarcity is a problem with this material, but for example, in the case of the thermoelectrics material, apart from the large Seebeck coefficient, a good electrical conductivity, and for example, a small thermal conductivity, and present for example, excellent thermal and chemical stability at high temperatures. For this reason, is a good solution for using concentrated solar technologies. But the scarcity of the material, I don't know if a problem. According to Jorge, it's not
Maybe
the problem.
for one kind of materials is a problem. Maybe not of all of material, of course.
Okay.
Thank you very much, Jorge and Roberto. We have another question from René Dominguez. Well, he's saying congratulations. Thank you very much, René. In terms of applications, how far is the use of this kind of materials in the medical area? Very interesting.
Oh, Rene, it's interesting material for me, especially because another topic of research is microfluidics with application in medicine, biomarker, etc. And I'm trying to combine this kind of understanding of thermoelectrics, for example, for cooling or heating devices, and especially like a sensors. And maybe one of my slides show some examples of wearable sensors. Now I'm trying to develop like a bracelet, like an example that I'm selling in the web, that you can monitoring some what do you see, fragility, maybe is the name. Let me check. It's fragility. I'm trying to check how is the response from this bracelet with this sensor inside to this kind of interesting topic that is fragility for the old people, for example. I think it's interesting. For now, just exists some equipment that, like a chiller, for example, a warmer, that works with this kind of materials or with these principles. I don't know if you, Diego, can talk on other things.
No, it's okay. No, I agree.
Okay, no comments, no more comments? Okay, thank you, Jorge and Diego. There is another question. This is again related to applications. What would be the difference, Jorge, maybe, in order to further understand for us, what would be the difference among electronic and photonic systems? You mentioned something about that in your research.
Photonics. Okay, it's interesting. I'm not study deep with photonics, but in this case, electronic for this kind of application is interesting. Photonic, I'm not a specialist in that topic, but electronic and thermal in this case is a key interesting understanding to improve the transport properties. Of course, you have that I showed you before, two kinds of focus. You can focus only in electronic or only in thermal, and the combination is the challenge. But maybe with photonic you can see some application with you combine this kind of material, for example, with the thermophotovoltaics. And in that case, you need to work with for example, combined with the theory of Maxwell, and improve the spectrum, and and other things. But I need to learn about that a little bit more to understand, to respond very well this question.
It's okay.
But I mean that way.
Okay, no problem. You mentioned that you did the research on this called two-dimensional materials.
Yeah.
And you analyze the lattice thermal conductivity of those two-dimensional materials.
Yeah,
why those materials and why not others, in order to understand?
Okay, I studied before the bulk materials and 2D materials, both. And with the 2D materials, you can obtain a better transport properties with the small structures. I think in a few layers that two materials have, for example, graphene or others. And I found some improvement in transport properties. And in that case, for us, it's interesting to understand that behavior, because the application is, I think, is more interesting, and the world or researchers in this topic are moving to the understanding and how and why this 2D materials has a better performance, you see, for some applications. And another kind of material today that the community studies sense, and another thing, all with the structures like a 2D, for example, where you can study, of course, the thermal properties of electronic properties or optical properties, whatever you need. And in this case, for this research, we study both electronic part and the thermal part. In the thermal part, interesting is to understand what happened with the lattice thermal conductivity. Okay, that is due for the phonons, for example.
Phonons, okay. You mentioned that thermoelectrical properties can be expressed by this called Seebeck. Am I pronouncing well? Seebeck coefficient, electrical conductivity, and electronical thermal conductivity. Is that okay? I think I understood well. Please, it's not my field of research, so I'm trying to. Is there any material or the one that you analyze that have some or less the optimal combination about these thermoelectrical property values, and if this material exists, if it has not been well developed to technologies yet, something that you think that maybe could be missed, in some kind of material that could be missed, that have more or less the optical combination of properties, thermoelectrical properties.
If I understand, the big problem, I think, today is a better combination of these three kind of properties. You can find, for example, a very good property for electrical conductivity properties of material like vanadium dioxide, but you don't have very good thermal conductivity. Very, very good for me is lower values of thermal conductivity, you see, to obtain higher values of figure of merit. And that combination is not very good. It's complicated. I know. I think it's not very good. No, it's complicated to obtain now. Or to found that, and that is a challenge, and that is what I explained before. Some research are focused on electrical properties and another focus on thermal properties, you see, but separate both. Okay, and I think the most studied are the thermal transport properties in this case, in this kind of material especially, you see.
Maybe Roberto and Diego can do some comments about that. Can you?
Yes, Jorge has shown that at least for the materials he analyzed, the tin selenide is the most promising one. you know,
Yeah.
with the best combination of these properties.
Yeah, of course. And there is another question related to this tin selenide. Is this material being applied already to some device, some wearable that you show us to us?
I'm not sure. I'm not sure. Yeah, I think so, but today, yeah, the study was related with the research and the papers and some projects, but yeah, at this moment, I've never seen some application with this kind of materials. The most common application materials in this case is bismuth telluride.
Yeah.
Okay.
Roberto, can you tell us?
I have a question to Jorge. According to the thermoelectric material, what is the best material to use in this application?
In my application is tin selenide, and
yes,
but I think as researchers in general is another kind of families. For example, as I told you before, bismuth and telluride, and yeah, and another combination of with telluride and selenium, of course, and sulfide too. And another interesting for us, I think, as a country, could be the combination of copper and with, for example, selenium or lithium. Maybe could be very interesting to explore. Some researchers just explore it, and exist some publications. And the figure of merit at this moment is close to 2.5, I think. And that could be interesting, almost for our country, because we have a lot of this material available, you see.
Okay, in the case of the phonon glass electron crystal.
What is the combination is?
Yes.
Let me check.
According to the behavior the behavior of the thermoelectric material. A behavior similar to the phonon glass electron crystal.
Maybe oxide materials are currently interesting to work titanium with sodium and another kind of combination. Maybe that could be works very good. And another perovskite too, strontium titanide oxide, and another combination of material. I think that could be a very good result in the phonon glass electron crystal.
Okay, thank you.
Is there well, most of the some questions that we got from your presentation, for me in my case, are related to energy applications. I'm sorry about my biased question, you know. But is there any device for energy conversion using those two-dimensional materials already? You mentioned that, okay, some of these may be very interesting for power electronics conversion in order to increase to decrease the heating of the switching of the the EGBTs and that sort of things. And do you know that this is something that is already being applied on power electronics, for example? Sorry about that question, but it's
I'm not sure in the industrial application, but yes, in the laboratory, some publication of that for cooling, for example, that systems. And now I don't remember what the specific paper, but I see before almost 2 papers related with that topics. And in the converters, I think, the thing. The same way is to understand what I can applicate this as a cooling system. I think that is the interesting topic for you, for example, in your research, and for electronic or electrical research that I talked with you before. I think that could be very good, but we need to test and prove this.
Okay, thank you very much, Jorge. Your topic is as you can see, there is a lot to do research on. There is a lot of space to do more research on this area. It's a very I think it's very clear to all of us that this is a topic that is a very cutting edge topic. There is something that is something very new, and something that has a very high potential. I would like to thank you, Jorge, for your presentation and your answers as well. And we'd like Roberto and Diego to give your final comments about this topic in order to close this presentation. Please, Roberto, can you give us some final comments? Roberto?
Yes, okay. I think the future expansion of the thermoelectric energy conversion technology is tied primarily to improve the materials, this performance, and with better thermal management design. This is my comment.
Thank you, Roberto. Diego?
Yes. Yes, I want to say that this topic is really interesting in terms of research, because there are many fields or many interdisciplinary fields that you can tackle within this context. I mean, Jorge showed that he worked with some DFT simulations, but you also have phenomenological simulations, different kind of simulations. I mean, from the nanoscale to macro scale. And also, other challenging aspect is the experimental part of it, just to validate all these results. So, and of course, as a result of this, of all this procedure is the final application of all of these materials in different problems. So it's really a very, I think, interdisciplinary project that in which you can find physicists, mathematicians, and engineers at the end.
Thank you very much.
Sorry?
Thank you very much, Jorge and Roberto and Diego, for your very interesting presentation. As I said, it's a very new topic, and I'm very interested with a very high potential for all of us. Thank you very much. Cristina, please.
No,
thank you very much, you guys, for this invitation, and thank you for all of the attendance.
Thank you.
Thank you to the panelists. Thank you, Ariel, also for the presentation. It's been a very, very interesting presentation. Different, and it has different from our main topic of our usual topic. and that I think is very enriching for the audience, who has been very interested, as we have seen, with so many questions. So congratulations to the three of you, and we would like to invite you to the next session, who will be held on the 28th of July. I'm sharing the banner. Just give me 1 second. There you go. Okay, so this session will be in Spanish, and in fact is energy transition, not only necessary, but also an opportunity. And it would be presented by Samir Cuoro, Jose Rodriguez, and Patricio Valdivia. So we hope you can register. In fact, right now we will send you the invitation too. And well, we will hope to see you there, right? So thank you very much to all. Thank you to the audience too.
Thank you.
Thank you all. Thank you all.
Bye.
Thank you. Bye-bye.
Bye. Thank you, Jorge.
Bye-bye.
Thank you. Bye-bye.